Hey, welcome back to your favorite calculus class. We're going to talk about sigma notation and limits of finite sums, and this is so that we can get a more convenient notation for sums with larger number of terms. Let's review a little bit your sigma notation. This is the Greek letter sigma. This is your lower sum. This is your upper sum. And this is the formula that you're using for kth term. You know, you're using k equals 1. A lot of the time you have an I right there. It just kind of depends on the problem. Um, So let's do one here. In fact, let's do that one right there. So you've got your summation from k being 1 up until we're going to let k be 3. We're going to plug it into this formula, negative 1 to the k times k. This becomes, so for k being 1, and then we're going to add in, we're going to do the same formula for k being 2, then we're going to do the same formula for k being 3. So negative 1 to the 1 times k, which is 1. And then we got negative 1 to the 2 now, because k is 2 times k, which is 2. And we got negative 1 to the 3 times that k, which is 3. Well, negative 1 to the 1 is negative 1 is 1, plus negative 1 squared is 1 times 2. Negative 1 to the third is negative 1 times 3. Anyways, we got this going on, which ends up being negative 2. So the answer to this is negative 2. So that's how you work that. You just start with your lower sum. In this case, you'd start with a k being 4, and you only go up to a k being 5 for that one. There's a solution there. So here's another example. So we've got k being 1. Whoops. K being 1. Let me plug k being 1 in. I get negative 1 to the 1. Cosine of 1 times 5. Now I got k being 2. So I got negative 1 to the 2. Cosine, my k is 2. So 2 times 5. And I got negative 1 to the k, which is then 3, because I'm doing k being 1, k being 2, k being 3, k being 3, and finally k being 4. So negative 1 to the 4, because that's our last one, cosine 4 pi. Okay, so let's clean this up. Well, negative 1 to the 1 is just negative 1. Cosine of pi is negative 1, right? You're thinking, what's the cosine of pi? Right here. Oh, the cosine's right there, negative 1. Negative 1 squared is just 1. Well, cosine of 2 pi is 1. Negative 1 to the third is negative 1. Cosine of 3 pi, negative 1. Negative 1 to the fourth is 1. Cosine of 4 pi, that's twice around, is 1. 1 plus 1 plus 1 plus 1. This ends up being, catch up here. Now, what if we're going to express it in sigma notation? So k being 1, or you could do I. Let me do k here. This is for k being 1, then k being 2, then k being 3, k being 4, and then for k being 5. Now you notice on all of these, so we're trying to write the formula here. We're going to start with k being 1. We're going to k being 5. Now what's the formula? Well, notice it alternates. Negative 1/5, then a positive, then a negative, minus 3/5, then a plus 4/5, then minus 5/5. So how do you get that thing to alternate? Well, it's kind of like this last one. This part will get that thing to alternate, the negative 1 to the k. The question is, if you want it to start out negative, you're going to have negative 1 to the k. If you want that thing to start out positive, then make that a negative 1 to the k plus 1. Okay, but this one's starting out negative there. And then it's going to just be that k number over, and notice it stays 5 the whole time, right? So notice for k being 1, I got negative 1 to 1, 1 plus is going to be, oops, k being 2 now. So we got negative 1 squared times 2. And my k being 3, 1 to the third, and 3 to the fourth. Notice that that's 3, right? And you see the spit this out right there. Okay, so there's your formula on that one. So you've got these rules for finite sums. You can add them, you can split them up, right? You just do the summation of that one plus, and you do the summation of the other one, you subtract it, you can put that constant out in front. Summation, if this is just a constant term, it just ends up being n times that constant on that one. So here's some formulas as well. Um, so the summation, in fact, let me show you this for example. So the summation of I being 1, you've got an I right there up to n. Let's let the n be 5. Now we know this is I being 1, or let me just go being 2, I being 3, 4. And we're going to plug in 1. We're going to plug it into the formula. Well, it's 1. Then we're going to plug in I again here. 2, 3. Okay. It looks like this ends up being 3, 6, 10, 10. Well, instead of doing that, you have these summation formulas from pre-calculus. I being 1 up to n of I will end up being n times n plus 1 all over 2 if you don't want to draw it out, right? Write it out and then do the summation. Well, in this case, our n is 4. So this ends up being, since it's summation of I being 1 up to 4 of I, this will be following the formula. It'll just be 4 times 4 plus 1, because again, our n is 4, all over 2. So the summation will end up being 4 times 5. 4 times 5, let's give me a here, 20 over 2, which is 10. See how that works? So for these special formulas, if you've got a constant or if you have just an I there or an I squared or an I cubed, instead of writing the whole thing out, you can just use the formula. Right? And of course, these are given in terms of I. Like I said, sometimes they use K. Like right here, they have a K squared. You're like, oh, K squared. I'm going to follow that one. I have a K squared right here. So that means it's N times N plus 1 times 2N plus 1 all over 6. Well, what's my N? That's my N. Let's set for some 13. So 13 and 13 plus 1 times 2 times 13 plus 1 all over 6. So 13 times 14 times 27 all over 6. And I think I got it written down here somewhere. That ends up being 819. Okay, so those are your summation formulas, and they will come in very handy. Here's an example where it can come in handy for you. If you're evaluating this, first you want to do it up to 10, and then they want you to do it after you do it for 10, then do it for 100, and then do it for 1,000, then do it for 10,000. Well, that's frankly quite a bit, right? So you can split it up. You can take this, you can split it up. You can say, well, that's the same thing as taking out the 1 over n squared part out in front, because remember, n is just a number right here. Put that out in front right there. And then you just have the summation of I plus 1. Well, summation of I, now you use that formula. Here's the formula for that. And the summation when you've got a constant 1 right here is just the 1 times the n. So 1 times n is just n right there. So I use the formula back here. So I've used that one, that's the 1 right here. And then I've used this one right here. Okay. And so it cleans up to this, and then you got to just keep working through that. Clean it up, and it ends up being n plus 3 all over 2n. Okay. So this I being 1 up to n, I plus 1 over n, cleans up to being n plus 3 all over 2n. Or if you want to think about that as 1/2 plus 3 over 2. It's the same thing. All right. So notice, if I'm going to let n be 10, now I just plug it in. 10 plus 3 over 2 is 10. I got 13 over 20, which is 0.65. Now if I let n be, instead of 10, if I let be 100, now I got 100 plus 3 over 2 times 2, 3 times 100. And that gives you that one, and so on. Okay. All right, let's go back to approximating the area of a plane region from last section. So on this one, what I'd like to do is I've got this negative x squared plus 5. And we're going to find, if you notice on the one on the left here, we've got the lower approximation using a right hand approximation on this one. So we use the right hand, each on these, right? The right hand for the height, right hand, and so on, right hand for the height. Whereas on the, and so this is this an under or an over approximation? Well, if I add up all these areas, it's not quite the whole area, right? I've got some little error in here, that, in little pieces of area that I'm missing. So this is an under approximation. Whereas over here, I'm taking the left hand, right? Left hand side, left hand side, left hand side. So I've got this over approximation. This one, over approximation for the left hand. Right? I've got the over approximation. Okay. So if we were to sketch this out, if we were to do the, let's do the right hand approximation. Um, First, you want to say, well, how many subintervals are we going to do? What's my delta x? What's my width on each of these? Well, b minus a over n. I'm going from 0 to 2. That's my a and b. So 2 minus 0, 0 to 2. And I'm splitting it into 5 subintervals. So here's my width of this, right? It's 2/5 is my width. Number 2 is, so I'm doing this one right here. So when I write this out, all my right endpoints will be 2/5 times I. Notice, because I'm going to use 2/5 and then 4/5 and 6/5 and 8/5 and 10/5 for my x value plugging in to give me the height there, right? So if I is 1, if I, oops, I is 1, 2/5 times 1 is just 2/5. If I is 2, 2/5 times 2, 4/5, and so on, right? So that's for I being 1, 2, 3, 4, 5. I being 1 up to 5, okay, for right-hand approximation. And by the way, make a little note here for the left-hand approximation, it would be 2/5 and it'd be I minus 1 because you'd want to start here at an x value of 0. So when you have I being 1, if you have 2/5 I minus 1. So when you plug the 1 in right here, you end up with 0. It starts you right there. So you go with the 0, and you plug in 2/5, 4/5, 6/5, and 8/5 for the left hand. So that would be for the left hand. But again, we're staying with the right hand, but that can be useful when you're doing some of your homework. All right, so let's do this lower sum. Lower sum. I call it lower s of n. So the lower sum here is, now I can use my sigma notation. I'm going to let I be 1 up to 5. My height is f of 2I over 5. And then my width, this is my delta x, it's a width of 2/5. Right? Width, 2/5, 2/5, 2/5. So this is my delta x right here. My delta x. Okay. So if you work this out, you know, for f of, let's let I be 1, f of 2/5, that's 2/5. That's 5 plus, and they do it for I being 2, plus you do it for I being 3, and so on. This will end up being 6.48. So we know this is in lower sum, right? We're missing some of that area. Now, if we do the upper sum, okay, so see, I lost my, the upper sum right here, right, we're going to be an over approximation. That will end up being 8.08. Okay, so this thing, the actual area will be somewhere between them, between 6.48, greater than that, less than 8.08. Okay, so what is the actual area? Well, we'll talk a little bit more about that as we make that a little bit more exact. Okay, so upper and lower sums here will simply be if we can make this into an infinite amount of those rectangles, we could have that, right? Going from A to B. So the region is bounded by the x-axis, the curve from A to B. Right? That would be our area. And right now we're just making a summation of all these rectangles, dividing that into n subintervals. Okay, and we would have a minimum value, like our lower sum, if we have those rectangles below it. We could have a maximum value if we are above it, depending on if we're inscribed rectangles or if we're circumscribed. In other words, over approximation rectangles. Okay, but that area is somewhere in there. All right, so we got this lower sum. Again, here's your notation. Your upper sum for the ones that I did. The upper sum was the left-hand sum. The lower sum was the right-hand sum. Okay, so the actual area is somewhere between the lower approximation with inscribed rectangles, the upper approximation with circumscribed rectangles. That's all that I want you to see here. Don't get too caught up in all the notation here. The actual area has got to be somewhere between them. We talked about how do you find your delta x, right? What's the width of that? B minus AL over 2n. So for this example here, if we're going to find the upper and lower sums of the region bounded by x squared between x being 0 and x being 2, let's kind of draw this thing. Okay, we're going to go from here to here, find the upper and lower sums of the region, and we're going to partition this thing into n subintervals. Okay, so number one, we're going to start with, we're going to say, well, our delta x is, we're going from 0a to b to 2 minus 0 all over n. I don't know how many subintervals we're going to split it into. You know, if it was 4 subintervals, for example, then I'd have a 4 right here, and each width would be 2/4 or 1/2, right? So that's the first thing, is what's our width on this thing? And here's some example. Here's with a few. Here's with looks like 5 subintervals on this one. Okay. So that's our delta x part. That's the 2 over n piece. Okay. And then if we're going to use the left endpoints, right, then we're going to have each, where would it be at? Go back here. The left endpoint, right, if I was to do it in terms of 4 subintervals here, I'd be going these, right? This would be our left endpoint. So this is the half, this is the 3, or 1.5, so 3 halves there. Okay, so the leftmost points. So you take the 2 over n and you put an I on it. For the left-hand subinterval, you're going to do an I minus 1 instead of just an I on it. So you take the delta x here, 2 over n, you stick an I for the right hand. If it's a left hand, it's I minus 1. So for example, for I being 1, I want to end up at an x value of 0 to use my left hand, right? So if I is 1, I got 2 over n. In this case, if we're doing it in terms of a 4 subintervals, 2 over 4, right? And then for I being 1, 2 over n. This thing's, now if I is 1, oh no. All right, I'm going to stop it right there and just have to merge these.